Okay, I think shall start today's session. Let's solve some questions and let's solve some uh, interesting questions. Meanwhile, let me first start sharing my screen so that we can get started. Okay, so I think yeah, let's go. Uh, right. Okay, so let's solve some. Let's solve the first question. This is the question I have. For that, I think I should first let's introduce to the session. What session are we at right now? I think we are in the ninth session of our series. This is a 12-week course. So roughly 75% of the course is done. We are towards the end of the course, and I think, yeah, so not many classes. Let's start then. We have been doing some problems, numerical problems in thermodynamics, and we shall continue today. And let's go. So this is the first question. An insulated piston cylinder device contains 5 liters of saturated liquid water at a constant pressure of 150 kilopascals. So what is the initial condition, initial state? So first of all, we have a total volume number with us. So V is like uh, 5 liters. So 5 liters, but 1 liter is 1,000 meter cube. Sorry, 1 meter cube is 1,000 liters. So 5 times 10 to the power minus 3 meter cube. So mind that. So this is what we have. Then we have saturated liquid. So it also says that we are at a pressure of we are actually at a condition of wait. So pressure is 150 kilopascals, and then to us, which should correspond to T. Also, wait. This is T sat, and at 150 kilopascals. That is what the temperature is. So we know the state of this initial uh, thing there. Give me a second. So now an electric resistance heater inside the cylinder is now turned on, and you have this much of energy transferred to the system. Uh, Now energy transferred to the system. Note that there cannot be any work done because given that this is not a flow process uh, and it's a control mass process, work done is zero. So delta U or delta E, let me put it this way, should be Q or yeah, Q. So energy transferred directly increases the energy, total energy of the system. In this case, because the kinetic and potential energies are not changing, so it is essentially increasing the thermal energy of the system. And that would mean that it's essentially temperature increasing and so on, and maybe pressure is also increasing because this is a piston cylinder system. So note, I don't know if pressure will increase or decrease. That we use that we will see. So first of all, it says at a constant pressure. So pressure is gonna remain same for two conditions. Oh, and another thing is insulated piston cylinder system. So that's also important. Essentially, there is no heat leak to the surrounding or anything. Whatever heat you are absorbing through the electric resistance is absorbed by the system. Okay, that's the reading there. Okay. Now, with that, you know that the pressure is not going to change for two conditions. That first of all, the piston cylinder system will have to will be exposed. The piston part of the system will be exposed to constant pressure because it will be like some weights must be kept on it or something, so that pressure remains constant. And it also explicitly mentions so. Now with that, tasks for us to determine the entropy change of the water during this process. Okay, so first of all, let's now we'll need to use property tables here. So let me pull up property tables to start solving this problem. Okay, so I think okay. So now without you guys, without showing you guys what tables I'm seeing, uh, let me. Okay, let me wait. Just give me a second. I'll pull up the property tables first. Mm. Right. So now I have the property table with me. Uh, First of all, let's calculate the amount of mass of liquid water in this piston cylinder system, which is not changing across the process. Okay, it's a control mass system. Piston is not changing. This mass is not varying. First, now for 150 kilopascals, T actually comes out to be 111.35 kilopascals. Oh, sorry, degrees Celsius. That's the temperature. Let's also find out the specific volume of liquid, which is 0.001053. This is meter cube per kg, which will imply that the mass inside this system will be 5 times 10 to the power minus 3 divided by. So this entire thing can also go into the numerator. Have 1.053 times 10 to the power minus 3, which comes out to be roughly less than 4.9 or something kgs. Let me just quickly calculate this. Yeah, 4.74 precisely. This is the mass you have. And now for that, delta U or will be 220 divide by 4.74. 8. Comes out to be 463.32 kilojoules per kg. This much energy you will have to increase. This is a very routine question. Now that we are in deep, like this deep in this question, we now realize that we just need to find out the final state, and that S minus SF will be the change in entropy. Okay, that's it. Nothing much there. Okay, now UF is let me let me calculate UF. Oh, sorry, from take it. Let me take it from the table. That's your UF, and so what do I mean by UF? UL. Let me put U initial. Let me put initial. U at x equals to 0 and 150 kilopascals. Now U final. So U final will be how much? You have to just add these two numbers. 930.29. One thing we realize that the liquid or the water will still be in a two-phase region. Why? Because something which I did not write here is that UG or U at x equals to 1 and 150 kilopascal is something that I could see from the table, and which is 2519 kilojoules per kg. So we know that the water has not been heated to fully saturated vapors. So we can actually rule out few options straight away by noting two things. SF and SG, the correct units, and let me put that unit also, kg Kelvin. So these are SF and SG. Entropy increases if you supply at a constant pressure you're supplying. So how can I say that entropy will increase? I will invoke PdV. Now you know that if your du is increasing and your dv is also positive, you expect entropy to increase. So actually, I can rule out few options. These two options have to be incorrect. Wait. It says change in entropy. So definitely this is not an option. But we can't still rule out other options. So by just that sheer logic, uh, I will find x first of all. So I need to find x now. That has to be what? That has to be 466.97, and this is the change in entropy. Sorry, change in energy. This thing 463.32 divided by 259, 2519.2 minus 466.97. X comes out to be 0.22. Just by that, I can find S equals to SF plus X into X into SF. So, but I don't need to calculate SF because I need to find delta S. So delta S is X SFG. SFG is known to me to be 5.7894. 5.7894 into 0.22 is 1.273. So roughly 1.273 kilojoules per kg Kelvin. This is what we're kind of roughly expecting. And the answer is close to it. It should be this one. Let me quickly check and see, tell you if we've done it correctly or not. Okay, wait. Seems like we've done it incorrectly. Okay. Wait. Let me think about it. What is the issue here? Let me think. Uh, wait. The entropy change. It's not specific entropy. Wait. So we need to multiply it with mass also. Maybe that is something that I have not done. It's kilo joules per Kelvin, right? Not kilojoules per kg per Kelvin. So we have to multiply 4.78 also. But then also the option is not set. Let me quickly check it up. Give me a second. 0.22. 7.2231 minus 1.431 0.2231 minus 1.437 0.221 plus 1.437. 68. Okay, so our X is roughly incorrect. You can check. Uh, okay, one thing which I forgot is it's a constant process, right? Oh, I'm making mistakes here. Like AE plus P dV, right? That is something I just totally neglected. And it should be minus. So actually we'll have to do it for delta H and not delta U. Okay, so a mistake is there. And if I accordingly correct all my further steps from that side, I can actually find my delta S, and it will roughly come out to be 5.72. So we were off because of this delta H issue. Okay, so now let's just quickly see why this delta H will come. Because it's a constant pressure process, no? I kind of missed the fact that there will be work done. There is no, I just assume that there will be no work done, but work done will be there because the piston cylinder system will move. So although the pressure will remain constant, volume is not going to remain same. So by just that logic, uh, that actually we could have had done this also, minus VdP, right? See, DH I completely know. It's given by that thing. And dP is 0. So actually we can find delta S very quickly. Uh, yeah. So it's 463.2 divided by 111.35 plus 273.15 into 2.748. Exactly. See, so we could have quickly had done this also. This is the simplest way to do it. Rather than we actually didn't need to do this entire thing. So what do I mean is ds or delta S T. So if you just divide 200 to 2200 divide by 111.35 plus 273.15, you get 5.72. Yeah, I can show this part to you. I'll quickly show this part. We don't need to do it this way. The quick way to do it is first realize that T delta S is delta H minus V delta T. Now, also realize that delta U equals to the Q minus P delta V, and this might as well be written as delta U plus P delta V Q. Now, because delta P um, 0, it follows that Q equals to delta U plus P. So it will follow that delta H will be delta U plus P delta V plus V delta P. Okay, uh, which is equals to delta. This implies that delta H will become equal to Q. And so from that logic, T delta S, because this is an isothermal process, isn't it? So T delta S comes Q, and this can simply be written as delta S is Q by T. So we just need to find T. Now T is known to us. Now actually to find T, so to even write this thing, we actually had needed to calculate delta H and all that. Only to later, yes, see, you don't know that this will be an isothermal process altogether. If you provide more heat and this process goes to super saturated conditions, then you can't apply this. Uh, but yeah, we think then we keep on applying this, even if it is super saturated. Yeah, then the issue will there become that we are not known that T remains constant altogether here. So here, uh, the fact that T delta S uh, is equals to, see what I mean is, if you have a saturation dome, you have a saturation dome, right? And you try to, like, say you are here and you move till here. So here, temperature was constant. Your entire system was at a constant temperature. So the entropy change is actually equal to Q by delta Q by T. Move in saturated state. Now along this line, temperature does not remain constant. So now what is the issue there? Uh, Great. Then you can apply this. See, then also you can keep on applying this logic because temperature is constant no matter what. Then here, this T delta, right? Temperature is constant. You can keep on applying this even here in this region also. We actually need to apply only this. If we are, wait. In this region, temperature is not constant, right? So in this region also temperature remains constant. Pressure does not remain constant. Okay. So in this region, you cannot maintain constant pressure and constant temperature. So you are not moving in this direction, but essentially you will have to move somewhere here. So in this part of it, uh, or if you're here, let's say you are somewhere here. Between this point and this point, this thing will still hold, right? If you move somewhere here, even then this will hold. So in that case, delta H will still be Q by T. But what T here? In this case, I know Okay, wait. Yeah. So the issue there will be that this cannot be integrated like this. Mm, I think in this part, temperature does not remain constant. So, right. So in this part, it actually has to be this. It cannot be just simply. So it will be somewhere like ds will be dh by t. And now how your h? So now this will be integral this thing dh by t. Okay. That case, this will not remain applicable. So we actually need to first find that it still remains inside the dome. But as soon as you know that it remains inside the dome, then you can use this formula to then see quickly calculate. Now, if you put 2200 divided by the temperature, which was 111 degrees, you put it in kelvins, you will get 5.72. That is what I'm trying to say here. Okay. Okay. So now let's look at other questions. Um, First question. So initially we'll do some objective type questions. There are four options. Decide which one we want to select for a reversible heat transfer and process being adiabatic. Process being adiabatic for a reversible heat transfer. Okay. And process being adiabatic, which of the following is true? This is true for a reversible heat transfer. No, this is not true for the reversible heat transfer. Mind that. Uh, A and D are the same options. Sorry, B and C are the same options. And this one, uh, for a reversible heat transfer, uh, this is not true. But for a process being adiabatic, this is true. But for a reversible adiabatic process, ds is also zero. And so all of them will be true if both the conditions are true. So in that case, all of them above is the correct answer. If it should be written as for a reversible process, okay? This does not at all make sense. Okay. the first question. Then let's look at the other question. So the following does not represent an example of high grade energy. High grade energy means someone which has a which is not heat. Okay, heat is low grade energy. So electrical energy can be completely converted to work. Indeed, right? Indeed, from a thermodynamics point of view, indeed that is what essentially we are doing. Although there will be losses also, but those losses are generally small. So it remains to be uh, high grade because we are essentially converting everything into electrical energy. Okay, that is why we are calling it. Uh, anything which can give you work, 100% work, that is called high grade energy. Uh, Although electrical energy gives you 99 something, there'll be some losses, but in principle, you can have a zero resistance uh, wire and then you can convert it, right? Um, but heat, even with all kind of assumptions, you can't convert it from 100%. So even if I'm considering uh, situations, electrical energy remains to be high grade. Okay. What about hydraulic energy? Still, it is a form of kinetic energy. So this is also true. And geothermal energy comes in a form of what do you say? Uh, it's a low grade energy, and kinetic energy is also what do you say? High grade mechanical energy, right? So the true option is that this is not the. So this is the true option, though. This is the correct option. All others are actually high grade energy. Okay. Let's look at the other question. State whether the following statement is true or false. Okay. As corollary, as a corollary to the second law of thermodynamics, complete conversion of low grade energy to high grade energy is possible by a heat engine. That's false, right? That is utterly false. It's the opposite. You can convert high grade energy to 100% to low grade, but not the other way around. Okay, that's false. Uh, Wait. So this is the correct answer. The statement itself is false. Okay, so true is not the correct answer. Say you are mixing Okay. We need to tell the relation between N delta S1 is greater or whatever. Okay, this is the option that we are looking for. So you're mixing 2 moles of this methane with 5 moles of carbon monoxide. And then delta S is 2 moles of hydrogen with 5 moles of nitrogen. Mixing entropy of mixing, change in mixing entropy of mixing. Yeah. So now we need to find this thing. Okay, so first of all, let's understand why what is going on in a mixing process. Okay, say you have one gas, gas number one, which follows this ideal gas law. Let's assume two ideal gases are being mixed. So R1, P, and then PV goes to R2 of P. These are both what do you say? Tensive properties, right? Now, if I convert this into um, amount of mass, um, with MR, let me put it as A and B. Amount of mass you have. Okay. And let's say both are at same pressures and temperatures. Okay. Now, because this V will be different. Okay. Let's say V will be different. So at a constant pressure and temperature, the volume two gases occupy are different. And that depends on the mass of that gas and also the gas exponent. Okay. Uh, we also know that R universal. So this is RA is actually R universal. So let me put it as R naught or something by molar mass. Okay. So let me put it as this thing. And let me put this as small m. Just tell you what is going on. Now, if you realize m b by um, moles, this is actually moles, right? mb by mb. You can write it as mb by r naught. This is universal constant. So let me put it as ru. And similarly, this will also follow. Now, um, if I divide V by NA, so V by NA, V by ND. So you note that if a pressure and temperatures are same, this V, the volume it occupies, directly proportional is constant, which depends on your pressure and temperature. Okay. Now, suppose you mix things. Now you have mixed some amount of what do you say? You have mixed two gases. Now what happens? So we should have an ideal gas. We should have a equation of state. So, uh, so uh, well, that's real when you mix it. When you mix things, you will have some volume Vf. Okay. if you mix the two gases and bring it to the same pressure and temperature, and it occupies Vm. Okay. So now we expect uh, so what do we expect is that the pressure, this should still follow. Still remains an ideal gas, right? This is something empirical. Okay, note that this is an empirical thing. One more thing that I know is that Nm by conservation of mass will be Na plus Nb. Now, what does this imply? Uh, this implies that ppm P uh, what do you say? PVA plus PVP. What are we essentially saying? We're essentially saying that when we mix, so the two volumes will just simply add up. Okay, and now this is the part. Individually, a gas was occupying a smaller amount of volume, and when you mix it, it is kind of expanding without giving you any work. You know that when a gas expands, like in a turbine, it gives you some work, it gives you some exergy. That is lost when you mix it. And that is why delta S has to increase. Okay. Now, uh, okay. Anyways, so suppose you were at, say, you were somewhere, you uh, have a system where you have two gases separated. So what will it as entropy be? We know that uh, TdS is dH minus VdP. For an ideal gas, this becomes as Cp ln P2 by P1 minus R ln P2 by T1. When you mix a gas, or I can also use this, isn't it? Okay, there is another catch here because this is R. There is a catch here. Actually, if I go ahead and drive this, the change in entropy of the mixture, as I was saying, suppose that you're mixing things. Uh, Delta S M uh, will essentially become RU, because you're expecting option here is, I'll just tell you what the option here is. Is actually just this, okay? Because RU, as I told you, sum over I. Then you just put Ni, where is N is your number of moles, into ln of uh, Ni by N of mixture sum. Okay, so let's do it from the first case. This will be minus Ru. Then you do sum. What is it? 2 divided by 5. 2 ln 2 divided by 7 plus 5 ln 5 by 7. Is this okay? Uh, and in the other case also, the same thing is there. So delta S1 will be equal to delta S2. That's it. That's the answer. So we have here is that's it. That is what we have. Got it? I think that's it. Okay. Let's move to the next question. Just quickly note the answer of this. Correct answer here is 0 because this is a cyclic process. That's it. Second question. If a reversible process occurring in a system reaches dead state at its final state, then irreversibility is. Because the process is reversible, irreversibility is 0 then. Okay. Okay, so now we have some good questions. Let's do them. What is the question? Question is steam enters a turbine at 9 megapascal, this much temperature. This is the speed, and it leaves at this pressure, this speed. Moisture content is given to you. So this is like X equals to 95.95. The turbine is not adequately insulated. So we know that there's some heat transfer that is going to happen. Heat loss is told to you. The power output of the turbine is 3 megawatts. Assuming the surrounding to be 25 degrees Celsius, determine the reversible power output of the turbine. Okay. Let's draw the let's draw the TS diagram first. So we are something kind of expecting this to happen. This would have been the reversible process, but something of this sort is going to happen. Okay. So we know initial state, final state. We also know the isentropic process. Okay. What will it have? What will happen? But we don't know the final pressure. I think we don't know we know the final pressure. We know the initial pressure. We also know the content. So initial and final states are all known. Uh, so heat is also known to you. Power output of the turbine is also known to you. Assuming the surrounding is 25, determine the reversible power output of the turbine. What was the maximum power that you could have what do you say? Obtained from the turbine? That is what we are trying to get here. Okay, let's do this question. Energy balance kind of thing that we can use here. Okay. This is what we have to write here. Just give me a second. First of all, this is a steady flow process. Okay. So steady flow process means that there will be some exergy destroyed, right? Uh, okay. So now, what is this? Okay. Then there will be some exergy of heat and work also. That will be because you are losing some exergy. Some Q, and then there is some exergy work done is also there. What is 5? Phi is equals to H minus T naught S plus V square by 2 plus GZ, but there is no mention of potential this height, and also at potential energy we are not considering. Otherwise, potential energy will also come. Uh, Okay. Another thing is we also need to find m dot. So first law also we have to apply. First law will be, so first of all, let's figure out what is the initial enthalpy and the final enthalpy. H initial, H in is what? So I'll just use the property table. Okay. So 9 megapascals. Um, and then the temperature is 600 degrees Celsius. So corresponding to that, I have few data. Okay. At 9 megapascals, 600 degrees Celsius. We have few things to note. 0.042861 meter cube per kg. We also have an HNS P63 4.1 kilojoule per kg. Have S just 6.96 kilojoule per kg of gallium. Now, at 20 kilopascals, X equals 2.5. Let's also figure out first of all P. So we are at 20 kilopascal. Okay. Pascals, T will be 60.06 degrees Celsius. And I actually need to calculate H will be 0.32832 plus 0.95 into 7.0752. Two 0.0752 5 is 0.832 is 7.55 kilojoules per kg. Well done. Um, that's okay. I'm just sorry, don't mind. What is H? H I'll quickly calculate without showing that step. 251.42 into 0.95 times 2357.5. 1.42. H is actually 249. 1.045 kilojoules per kg. What does the first law say? First law says that delta H equals to delta kinetic energy minus. So from here we will find out m dot first of all. So m dot q dot is 180 kilopascal. Again lost. Okay, this is minus. So we can actually take out the minus common. 180 kilowatts plus 3000 3180 divided by this difference. What is it? 24 says 363 4.1 minus 249 2491.045. How much is this? 3180 divided by 363 4.1 minus 249 1.045. This is 2.78 kgs per second. Okay. So first of all, we figured out the mass flow rate. That is the first thing that we actually need. Then we also need to figure out this T business. Heat is lost. This should be equal to P naught dot now. So from here, uh, let me think. Um, okay, and there will be another thing which I have not included here. This will be delta H plus delta K, which is V square by 2. That I have not done. Let me do that also. So that will be a minus, okay? 60 square minus 90 square by 2. Great. So initially, put entropy. So delta H decreases, but kinetic energy increases. Okay, yeah, that's okay. So minus 2.2. Nothing very expensive. So that won't change the answer very much, but okay, that's fine. 363.4.1 minus 249.045 minus 3.5. So still remains 2.78. Let's see here. Can quickly calculate our also I'll calculate quickly 2.78. Let me take T naught common so that because we need to calculate XLG. T naught can come actually here. Delta S is actually 2.78, 298, delta S 7.55 minus 6.96 minus 180 kilowatts is 308. Um, plus 3. Right. So now if this is calculated, no, this will come around 668 kilowatts. And so now your reversible work is 3000 plus 368. So that will be the answer will be around this. Actually. Answer comes around 3668 kilowatts. This is your first answer. Take 5 to 10 minutes of break and then I'll come back. I'm thinking, why not close it here and uh, not every one of you is available also. Like you're not there, no? So it is better next time. Probably you will be there, so you can do it then. I think. Next couple of questions. Yeah, so let's pick these things up next time, and then we'll finish it up. Okay. Okay. So meet you next time. Let's close now.